for the first part of the lecture, I explain what transfer learning is. I give you lots of examples, engineering or not. Hope you help you understand why we need to do transfer learning. In the second part of the last lecture, we went through some different settings, like what is domain shift, what is homogeneous or heterogeneous domain adaptation. We also went through different settings in terms of the data label availability. What do we need to address? Supervised, semi-supervised, and unsupervised domain adaptation. So in the second part of the lecture, before we having lunch, we will go through several topics related to image analysis, or in particular for image recognition. And finally, after lunch, we will go into the third lecture, which focuses on image analysis, image manipulation. Okay, so let's start the second lecture of today. So the second lecture, like I said, we will focus on image classification. Image classification, and particularly in case where we can only collect data, we can only have data from the source domain, the label data from the source domain, but we probably do not have label data in the target domain. Well, let me see if we can get rid of the symbols down there. Okay. Okay, anyway. All right, so the first one is face recognition. It makes pretty much sense, right? Like I said, if we need to do face recognition for a particular group of people, we probably do not want to always go ahead, recollect the data, annotate the data. We want to go out and borrow the information, borrow the label data from other places. And you know, for face data, there are lots of publicly available ones like CMU Pi dataset, multi-Pi dataset, LFW, CELEB-A. There are many existing large-scale data sets which can be used to train your face recognition classifiers, or you can train your good classifiers to determine what good features to use. So that is one case. So the second case is, we also mentioned this earlier, for medical imaging. In some cases, you would think that, for example, we know the MRI machines are extremely expensive. So for the MRI machines, not all the hospitals are affordable to buy such machines. So what if they have only a limited amount of budget? They would buy the MRI with fewer resolution, or even only CTs or other different kinds of sensor images. So what they want to do is still to do good classification using the data, maybe with less resolution, maybe with more maybe noisy data, etc. But can they borrow the information from the images with high resolution, with clean data, etc.? So this is also a possible direction, a possible way to do good medical image analysis using a limited amount of data, or with the data, or using the data with limited budget, etc. So these are all the scenarios which we need to do visual classification. Well, another interesting thing is many people would like to do food image recognition. Some would like to see what kind of food they are eating. Some want to calculate their calories, right? So is it possible that we can train our classifiers from the raw data? And eventually, well, this is a little bit fancy, you know, but anyway, but can we do recognition of the food composition, calorie, nutrition, etc., from the target domain images? That is also a possible way and interesting people would look into. Okay, so if you were awake in the first lecture, you would remember for classification, we have different techniques to deal with the domain adaptation task. So the first one is instance transfer, right? So recall that if we have source domain data, source domain labeled data, and we also have target domain label data. We all have label data available. Then we need to identify which instances in the source domain are informative. They are helpful for transfer, for designing the classifier for the target domain. So that is considered as the instance transfer. Okay, and for the second one, for the feature transfer, feature transfer, that is, we have maybe heterogeneous type of data, images and text, right? So we need to transfer, we need to convert the data. We need to map the data onto a common feature space so that we can design our classifiers, we can do recognition in that common feature space. So that is considered as the feature transfer. Okay, and finally the parameter transfer, that is when we train the classifiers from the source domain, can we gradually adjust some parameters? Can we gradually adjust the model so that it would fit our target domain data, which is considered as the parameter transfer. Another thing which is catching people's attention recently is the classification, is the learning of the classification model based on some prior knowledge, based on some relation which you observed from your data. And that is particularly interesting and helpful when you need to do few-shot learning, one-shot learning, and zero-shot learning. Okay, so in case you haven't heard of any of them, we will briefly talk about these settings maybe in the last 30 minutes or so in the second lecture. Okay, so these are the commonly seen techniques for doing classification in the transfer learning in the adaptation case. All right, so again, this table just for your reference, and later when we complete the entire lecture, I believe it would make more sense to you and come back to see which one of them fits into which category. Okay, so I think we can skip the first few slides because we just went through this in the first lecture. The first one is instance transfer. Okay. Oh, so there's one more thing I should emphasize is instance transfer, there are two ways to do so. You can do it the hard way or the soft way. So obviously, the hard way is you simply pick that instance to be considered or not. You simply select the instance to be transferred or not. And that is the hard way to do the transfer. And the soft way is to do the data reweighting. So basically, when you borrow the data from the source domain and retrain your classifiers, you do not treat each data equally important. You need to learn how to give proper weights to each data instance. So that is called data reweighting. So anyway, when you need to look into instance transfer in the future, you should remember there are two different possible solutions. You can do simple data, well, it's not that simple either. You can do data selection, or you can do data reweighting, depending on which kind of method is easier or which setting makes much more sense to you. Okay, and the second we just went through as well, the feature transfer to deal with the heterogeneous data. And I think I can highlight one simple way to do feature transfer. I think one of you asked me during the break, like using the example I just gave you, well, we have image data in the source domain, and we have target domain data we have text data in the target domain. So in that case, how do we know whether I should project the data into a common feature space, or should I project the image data to the text domain? Or should I project the data from the text to image domain? Because either way, or one of these three possible solutions, you will observe a common feature space anyway, right? So how do we know which way to convert, or should I create a totally new, a totally different common feature space? Well, although there's no clear or definite answers to this question, but I can give you a general guideline or general idea. So one thing is you probably want to project the data from the domain with higher dimension to the domain with lower dimension, right? Because that way, you will probably easier for you to preserve particular information. That is possible easier for you to calculate like the structured data information in a lower dimension space instead of calculating the distance, the locality information in the higher dimension space, right? So the first rule or the first guideline or the first suggestion is to convert the data, to map the data from the higher dimension space to a lower dimension space. So depending on the features you are using, maybe you are using the CN features for the images, it's like 4,000 dimensional features, right? Maybe you are using word embedding or some existing semantic features is only like 128 dimensional feature vector. In that case, you will probably map data from image to text. Or you can map anything to another new common feature space with 128 or any dimension lower than that. So it is possible. Okay, so I hope this addressed the questions, or for some of you, how do we know which way to transfer, or what is the preferable way to transfer the data? So once you transfer the data, then you can consider whether you want to design which kind of objective function you want to design. If you have label information for your projected data, you can design the objective function. You can design a CN classifiers or just the standard classifiers, trying to minimize the classification loss. Okay, so beyond classification loss, what can you consider? For example, contrastive loss, right? For the data of the same type, after the projection, you want the data to be as close as possible, right? For the data of different types, if one is computer, the other one describes the bicycle. After the projection, you want them to be as far away from each other as possible, right? So that is the so-called contrastive loss. So there are different kinds of classification or identification or locality loss you can consider when you do this kind of feature transfer-based domain adaptation algorithm design. Okay, so this one is pretty straightforward, I think. The first one is they compute the transformation matrix, mapping the data from one domain to the other. And after the projection, they simply have the similarity loss, like I just suggest. For the data type of the same, for the data of the same type, for the data of the same category, they should have higher similarity. So this is a straightforward conversion from mapping data from one domain directly to the other. And after the projection, because they do have the label information for source domain data, or because they have the label information for specific selected data, so they can enforce this similarity loss or the distance loss to make things happen. Okay, so this is one example for feature transfer. Now let's get back to the first challenge in domain adaptation. So recall that it is the domain shift, the domain bias. We need to get rid of the difference between the two domains when we borrow the information from one to the other. So that is so-called the domain shift or the domain bias. And recall that in the last lecture, we said that even before the use of the deep learning, people start working on getting rid of the domain bias. They calculate the MND, and the definition is very simple. They simply minimize the difference between the projected data means, right? And as you can see, when you calculate the MND, do you consider the class information? No, right? Because when you calculate the mean for the source domain, you simply consider the global mean. You do not consider any class-wise information. Similar remarks apply to the target domain. When you calculate the data mean for the target domain, you simply calculate the data mean. You do not consider any class label information. So this is a very straightforward solution for getting rid of the domain shift, because you can do this for supervised, semi-supervised, or even unsupervised domain adaptation. right? You simply define your transformation function, and hopefully, after the data mapping, the difference between the projected data means will be as small as possible. Okay. So saying that, what is your idea? If you are a researcher in this field, what would you do in the next? If you know getting rid of the global mean difference would be good, what is your next idea? If we have some label information in the target domain, would you think, why don't we not only making the global means closer to each other, why don't we also make the class-wise means to be close to each other as well, right? If we can do that, maybe we can do an even better job for this cross-domain recognition task. Because you can imagine that making the global mean matching each other, it doesn't really say anything about class-wise distribution, right? You can imagine that if we have a source domain data distribution look like this, and if we have the target domain distribution look like this, if you make the domain means close to each other, yes, they are close to each other, but the distributions are still very different, right? I don't know how to make this more easier for you to understand, but anyway, it only makes the global means close to each other, but it doesn't make the distribution really overlap with each other, right? So that is what I'm saying, that if you understand what we have been talking about, and you should have an idea for the next step, why don't we also make the class-wise means close to each other as well? But of course, the next problem is, what if we have only semi-supervised setting for the target domain data? What if we have no label information for the target domain data? In other words, what if we are dealing with semi-supervised or unsupervised domain adaptation? Of course, there are the things you need to address. And that is why you are here. You need to come up with good ideas to deal with this kind of challenging settings. Otherwise, you just need to learn Python. You just need to know how to train your models. Then that is the end of the story. Hopefully, it is not, right? OK. So the second equation, we also mentioned this earlier. We not only do this in the original linear space, we can also do this in the nonlinear space using kernels. So basically, this is the visualization of what happens if you do the global mean distribution match. Well, the basic idea, like I said, like back in 2011, that is before the high popularity of deep learning. Even in 2011, people started looking at this MMD term, trying to make the entire distribution of cross-domain data to match each other. And hopefully, using this, even without using any label information from the target domain, they can still do a good job in recognizing the target domain data. OK, so this is so-called TCA, but it's OK if you forget the term of TCA. But anyway, we are doing calculating the MMD, minimizing the cross-domain mean. OK, with the TCA, only the global mean, 2 years later, not surprisingly, people start looking at the class-wise mean as well. OK, and these people call them the joint distribution adaptation, the JDA. So they not only minimize the cross-domain global mean, they also want to make the class-wise mean close to each other after projection as well. But of course, they were addressing the challenging unsupervised domain adaptation setting. Remember what is unsupervised domain adaptation? That means for the target domain data, we do not have any label information, right? So in that case, how can they do global mean matching and also class-wise mean matching? Well, their idea is quite simple. Before I give you their solution, what would you do? If you want to make the distribution closer, if you want to make not only the global mean close to each other, you also want to make class-wise means to close to each other, but at the same time, you do not have any target domain label information available. What would you do?
Any idea? Use some sort of resampling and then make each sample's mean similar?
Yeah, I think the idea is quite similar to that. They didn't do resampling, but they do assign pseudo labels. They guess the labels for the target domain data. So it's quite similar. Okay, so let me refresh this again. So of course, they do not have any label information for the target domain data. So at the first step, they can only make the global mean close to each other, right? So after this, they can start predicting the label information for those target domain data. So once they predict the initial assignment, the label assignment for the target domain data, then they can also make the class-wise mean to be close to each other as well. And they can do this iteratively until the loads converge or until the number of iteration makes the maximum number, etc. Okay. Yep.
But why do you actually want the class-wise means to be close to each other? Don't you want to distinguish your classes? So you would like the means to be far away to make it easier to distinguish the classes?
That is true. So for the task of classification, the ideal case is you want the separation between the class means to be as large as possible. And at the same time, you also want the intra-class variation to be as small as possible. So that is the ideal case for classification tasks, right? So I guess the reason for them, because they came up with this idea, I guess the reason for them just want to match the class-wise mean instead of pushing away for the means of different classes is they need to deal with the domain shift at the same time. So they might not be sure when they push the data means the class-wise means away from each other, would they make the data bias larger or not? I think that is the reason. So they only want to make the global means and the class-wise means to be close to each other. Yeah, but that is a very reasonable idea, the motivation. Not only to make the means close to each other, and at the same time, we want to make the class-wise means of different classes to be away from each other, because that is the purpose of classification, right? Okay, yeah, so that is JDA. So again, if you forget the name, that is totally fine. Just get the idea of this picture. Making the global means to be close to each other, making the class-wise means to close to each other, and that is the idea to get rid of this domain shift. Okay, and for the unsupervised case, not only to predict the pseudo labels, other possible ways is, can we consider the local structure, the local information of your target domain data? For example, after you predict the pseudo labels for the target domain, can you refine your prediction based on the neighbor information based on the locality information of your target domain data? For example, if you have an instance of the target domain, which is called the class red, and it happens that two of your neighbors are also predicted the same category. The two neighbors of you are also predicted as class red. Then it is highly, highly possible that you are the same, you have the correct class prediction, right? So not only to do the pseudo label prediction, not only to do this kind of MMD stuff, the global mean, class-wise mean, there are other people. Oh, it's us actually. But anyway, so there are other people. They are considering to exploit the locality, the structure information when we deal with the transfer learning, the domain adaptation tasks. Okay, so this is the label and structure information during the adaptation process. And there are other variants as well, because when we talk about the exploitation of label or structure information, we can do that for homogeneous data. We can do that for heterogeneous data as well, like image and text or images with different features. But of course, because of the interest of time, we will not go into each details, all the algorithms, because maybe half of you would fall asleep. So we will not go into the details, the equations for each method. But anyway, the most important thing is what is the motivation of these people, and what are the general idea, general guidelines when they transfer the data from one domain to the other. So I can show you an example. What if we not only consider matching the global class-wise mean, but also consider the locality data consistency? Well, this is a good visualization who to make you easier to understand. So different colors in this figure indicates, I should say, different dots in different colors indicates the data of different categories. So there are digits labeled. So they are classes 1 to 10. Okay. And different shapes, you can see they are triangles and the circles. Different shapes, they represent the data in different domains. So after domain adaptation, what is the ideal case? The ideal case is that the data across two domains with circles and with triangles, they should be as close to each other as possible, right? And at the same time, data of the same category, they should be also very near, very close to each other as well. So you can see this is the example. You have the same type of color instances close to each other, and at the same time, you can see there are triangles and circles in it. So that explains we really can get rid of the domain bias, and at the same time, by making the class-wise mean, global mean and class-wise mean close to each other, we do make the separation of each class to be reasonable, and that is why it would be able to produce satisfactory classification performance. Okay, and we didn't mention this reweighting, but I did highlight the instance transfer in the first solution, right? We can do that in a hard way or in a soft way. And in the soft way, we do assign the weights for each source domain data to determine which of them should be transferred to the target domain and which of them should not be that important during this adaptation task. Okay, so this is the visualization. So in the future, if you are dealing with your own task of transfer learning or domain adaptation, not only show the numbers, you can plot your data in 2D. You can use PCA, or you can use TSNE, whatever visualization, dimension reduction techniques you want. You can visualize whether your projected data makes sense. And like I said, do you see the clustering results of the data of the same type? If you see the clustering results of the data across different domains. Okay, so this is the visualization of the standard non-deep learning-based adaptation algorithms using global mean, class-wise mean, exploiting structure, locality information, etc. But of course, with the use of the deep learning, many algorithms can be, I don't want to say ignored, but actually the recent development of deep learning algorithms really help in terms of transfer learning and domain adaptation. Because as you can imagine, using deep learning models, we would be able to extract very powerful features. And sometimes, not in all cases, but sometimes such features are good enough in describing coarse domain data. And later, I think we will have a table or two to convince you about this. So when we use deep learning models, some simple domain adaptation task does not exist anymore. It turns into a simple classification task. Okay. So do you have any questions before I move on into the deep learning part? Yes.
Can you go back to the previous slide, please?
This one?
Yeah, so when you're trying to minimize the difference between class-wise distribution, let's say so you have the triangles and the dots, right?
Right.
So the first class that you will, so when you try to do the pseudo labels, let's say you have the 10 classes for the target data. Now you need the information that class 1 in the target data matches class 1 from the source domain.
Okay, so your question is when, in this example, do we need the label information for the target domain data?
Yeah, you're trying to guess, right? You have a single target.
Right.
For the target domain. Now the question is, you know which class in the target domain corresponds to, let's say, the first class in the source domain? Does that
Oh, okay.
relevant?
Right. So again, the setting is, again, it is a unsupervised domain adaptation. So we do not have any label data for the target domain, right? So I think, so you're wondering, so since we start from an unlabeled setting, and we want to match not only global distribution, but also class-wise distribution, how do we know we did a good job in predicting the pseudo labels for those target domain data? Right. Of course, eventually, results-wise, quantitative evaluation-wise, it did a much better job than just global distribution matching or even non-adaptation task-based method. But I think there are two things you can look at. The first thing is, we just mentioned the MND, right? You can calculate, okay, I didn't want to go back to the few slides earlier. Now, we can calculate the MND, and that is the distance between the projected means. We can calculate that for the global mean, and also that for the class-wise mean. So you can observe whether or not during this refinement, this iterative prediction process, the MND really goes down. If it goes down, then it convinces you that you are matching the data across the two domains, global-wise and class-wise. So that is the first indication you are doing a good job in predicting the pseudo labels. Okay, and with that, you can calculate the final classification performance, like what we did here. You can calculate the final prediction error or the classification error for the target domain data. And additionally, you can also visualize the data like what we just did here. Okay, so basically, there are these things you can verify whether or not you are predicting reasonable pseudo labels.
For example, let's say class 1 is computer, or the source domain. Is it possible that after the projection of the target domain, you have a cluster that's very close to the computer class, the first class, but somehow it actually corresponds to bicycle. But they just happen to be clustered and they're very close to the computer domain. Would that affect the element? I'm not sure if you understand my question.
So are you saying that if we have some examples which are close to other types of data?
What I'm saying is, I guess when you do the class-wise, when you try to minimize the difference between the same class from two different domains,
Right.
you have to know that the two classes, they actually correspond to each other. Right? Now, my question is it possible that you have a situation where you have two classes very close to each other, however, they actually correspond in reality to
different classes? Yeah, of course it's possible. Of course it is possible. And yes, if that happens, of course it would make your performance worse. But that is why I said we need to check few things. The first one is the MND for global-wise MND, and also the class-wise MND. If both of them are decreasing, then which means we probably didn't see those kind of errors during the training progress. And the other thing, I think for reality is most of us would not deal with the totally unsupervised domain adaptation. I believe for companies, big companies or startups, although we cannot afford to annotate all the data we have, at least we can annotate 10% of them. At least we can hire some people, hire some interns to annotate 20% of them. In that case, that is semi-supervised domain adaptation. In that case, we will have much fewer chance to have those kind of error happen. Right, so hopefully that addresses your question. Okay, right. Okay, then we can move on to look into the deep learning parts and see how the deep learning people address such still somehow challenging domain adaptation tasks. Okay, again, I assume that most of you have background in deep learning already, so you would probably understand, agree, and feel comfortable that deep learning is a powerful technique. Once you throw in lots of data with ground truth level information available, it will be able to learn good features, good feature representation, and at the same time, it achieves very promising classification performance And such features, if you visualize them from the low level to high levels, you can see different information from local to higher scale information to be observed from your learned features. Okay, so that is a good thing about deep learning. So now let's see what happens if we start using CNN features to deal with the aforementioned classification, cross-domain classification tasks. Okay, so previously, people start using decaf features. It's very simple, standard, basic deep learning models. But when we talk about the Amazon DSLR, those office data sets, the data sets involves 4 different data domains to recognize the objects, right? So when we look at the office data sets, people start taking the CNN features and see what happens if we do nothing about domain adaptation, we just pick a more powerful feature. What happens for this object cross-domain object recognition task? Okay, so from this task, again, we are using decaf as the features to describe the images. And we have the images from like DSLR, Amazon, and webcams from these data sets. Okay. So how should we read this table? Well, for the left-hand side of this table, we simply use the standard surf features. It's kind of bag-of-word features if you are familiar with sieved, surf, those kind of image descriptors. But anyway, for the left-hand side of the table, they are the performance reported by different models using standard image features, bag-of-word features. And for the right-hand side of the table, they are the performance reported by the same models, but using deep features. Okay. So now let's look at some starting ones. For example, if we use the bag-of-word features, very standard features, and we do nothing for transfer, the rule means we do not use any more complex adaptation models. So A to D means we train our classification models like SVM, KNN, whatever. We train our models using Amazon data, and we do recognition on DSLR. And you can see the performance is extremely bad. It's only about 30% or so, right? Remember TCA? Although I say you don't have to remember. TCA is the match of global means, right? The first one using MMD to get rid of the domain shift. TCA, using the matching of global means, let's see what happens for similar tasks. Like for A to D, A to W, this kind of domain pairs, slightly improves or even just comparable performance compared to doing nothing, right? Comparing to the first column, TCA only slightly improved the performance. And again, that's why I said simply matching the global means is probably not a very good idea. And what happens to JDA? JDA is considering both global mean and class-wise mean matching, right? Using JDA, yes, the performance gets a little bit better, but not that impressive. But at least we're moving on, right? So JDA, again, gradually gets better because it not only matches the global means, but also the class-wise means. So these people work so hard using standard features. And the numbers are, okay, you get your paper accepted, or something like that. Anyway, but what happens when we move to CN features? You can see that for JDA, using CN features, the performance had a big jump from 30, 40 something to 80%. So you can see that using a more powerful features really help. So before the rise of deep learning, we, among these people, were really working hard and designing good models, try to transfer the information from one domain to the other. People work so hard based on a very bad or a very basic feature. Okay, and now using CN features, you can see that the domain shift is not that significant anymore. Okay, So what this tells you, this story tells you that sometimes picking a good feature is a really important task. And if you train your decaf from ImageNet or from this Office dataset, etc., they already provide you a sufficient ability to describe your image data. Even it might have an irrelevant or non-overlapping class. For example, if you train on the image datasets with the objects, but eventually you are using the model to extract the features to describe, to recognize the animals. Even though the class of interest are not overlapping, but because the features are very, very powerful, so in that case, you are still able to do a good job in this domain adaptation task. The domain shift, the domain bias is not that remarkable anymore. Okay, so hopefully this table gives you a good idea why picking a good features, why CNN is so powerful, so promising in many adaptation tasks. Okay, well, of course, not all the problems can be addressed by picking CNN features. Otherwise, we will just stop here and go out for lunch, right? So we will still go into some different variants and go into some different settings and discuss why we still need to explore some other possibility. We need to design good models, good features to address particular tasks of interest. That is what we still need to do. Okay. So we're okay with this table, with these results, okay? So now let's see what deep learning do in terms of domain adaptation. Of course, for this slide, they did nothing. We just used their features and using some existing adaptation models and see whether or not we can do a good job in recognizing such objects. But eventually, when they really are dealing with very, very different data, they still need to design good deep learning models to extract good features to achieve good performance. So this is the figure highlighting, illustrating the idea of MMD, right? So we have the data in the source domain, which are the data colored in red. We also have the target domain data colored in blue. And using the MMD we just mentioned, after the data projection, after the feature extraction, hopefully the global means will match. The distance between the global means will be as small as possible. And that is the way to visualize the minimization of MMD, right? So deep learning people said, well, it's a good idea. So why don't we add this idea? Why don't we enforce this idea into our CNN models when we design our CNN classifiers? In that case, I will get good CNN features, and at the same time, I guarantee you the difference between the global means will be minimized. Okay, so this is how they did it. So first of all, this is domain adaptation task. They are solving the same learning task across two domains. That is the definition. And second, this is a more challenging one because this is an unsupervised domain adaptation. Unsupervised because we only have labeled data for the source domain, and for the target domain data, we have unlabeled data. But again, realistically, you want to explore unlabeled data or semi-supervised, that is totally fine. But they start from the challenging one, unlabeled domain adaptation. So how did they design their model? You can see that first, let's ignore the right-hand side of this figure. So the left-hand side, it is a standard CM model. I forget it's VGG or some model. They just train this model from scratch because they have data, they have labeled data, so they can train this model from scratch. So the first few layers extract the features, and the last layer does classification, right? What about I present you a sufficient amount of unlabeled target domain data? What about now? Well, now you can see the right-hand side of this figure. It is exactly the same model because you can see the dotted lines here. That means the two models have shared parameters. So basically, it is the same model. But the problem is when you dumped in your target domain data, they don't have labels. They have no labels at all, right? So there's no way you can go to this final classification stage. So what did they do? MND. So for the source domain data, once they reach the feature layer, one thing is they go ahead to calculate the classification loss. You use the softmax cross entropy to calculate the classification loss. At the same time, because you will be able to observe both labeled, I should say, you will be able to observe both source and target domain data. So once such data reach the feature domain, you can calculate their global mean. And you can try to minimize the global means. I should say the difference between the global means, right? So we're all good so far? In that case, we have two losses which allow us to do backpropagation to update this model, even though for the target domain data, they are totally unlabeled. So you can consider this as a multitask learning. I think one of you also asked me this during the break. This can be considered as multitask learning. We are designing and training the same model, but we have more than one loss. We have more than one properties which we can consider, which can allow us to make this model better during this training progress. We have the classification loss from the source domain data, and we also have the MND loss. We try to match in the global distribution of the source and target domain data. So that is a very basic idea, and I think this is, I forgot this is published or not, but this idea came around 2014. Okay. So as you can see, the most important thing is the classification loss, at least for their task, at least for their data. The most important thing, they fully focus on the classification loss, and they adjust the weights for their MND loss. That is what they did in their model, the design of their model. Oh, okay, so they did publish this thing in ICCV 2015, which was in Santiago, Chile, okay, because I was there. Okay, so in ICCV 2015, they published their work. So basically, they just give more detailed explanation, but basically that is the thing we just mentioned. They have a shared model. They want to utilize the label information from source. They want to utilize the MND loss from both data domains. That allows them to design a good model to do the data, the adaptation parts. Okay, so this is the visualization and see for the same type of objects, but across different domains, whether or not they have similar confidences for the prediction outputs in this using their model. Okay, so the idea is quite simple, right? Just the combination of classification and MND. Well, they also did a little bit more things in this ICCV work. That is, they add additional sub-label loss. Well, I think, okay, but anyway, I think the most important thing is the classification loss only comes from the source domain data. And again, these are the shared models, so they just plot this in the other way, horizontally. So they have the classification loss, they have the domain loss from both data domains. And in some case, somehow they just alleviate their way to calculate the classification loss. But anyway, I think the most important thing is the integration of MMD and the classification loss. I think that's the at least the take-home message for this ICCV 2015 model. Okay, so another thing which is really, really interesting is this domain adaptation model, also based on deep learning. And this is the model which we will work on as your exercise in the last part today. Okay, so my two TAs will go through this model and have an exercise looking at the hand digit written data sets which allow you to practice the design, the training of the models, and see if your design model is able to address cross-domain recognition tasks. Okay, and yeah, so we'll get a hands-on experience for the last part today. Okay, so let me go through this model and see how this model addresses domain adaptation. Okay, again, we are dealing with unsupervised domain adaptation. Only source domain data are labeled. Target domain data are totally unlabeled. Okay, the same as the setting as the previous one. So what did these people do? This was proposed in ICML 2015, and later, yeah, it was in ICML 2015. So for the source domain data, it is exactly the same as the other group people did. They dump in the source domain data. They can train the feature layer, the green parts, right? And because the source domain data are with labels, so they can go ahead and train the blue parts because they can calculate the classification loss. So that is exactly the same as the ICCV 15 model we just mentioned, right? What happened for the target domain data? The target domain data are unlabeled. But for this group of people, they don't want to look at MMD. They might think the calculation, the minimization of the difference between the global means is quite a naive idea. So they didn't want to calculate to minimize the MMD. What did they do? Well, you can see that there is a different branch in this model. There's a pink branch in this model. And this branch, they gave it a name as domain classifier. Obviously, if you dump in the source domain data, source domain label data, the data rich, your features will be observed here, right? Then you can go ahead, not only go through the purple or the blue part to calculate the classification loss, you can also go down and ask the pink classifier which domain you are from. So for the source domain data, this output should be you are from the source domain. Doesn't matter what label you are with. I just want to make sure you are from the source domain. I just want to tell that, right? Similar remarks for the target domain data. For the target domain data, they are totally unlabeled. Once you go here, you cannot go the blue parts because you don't have any label information to calculate the classification loss, right? You can only go down, ask the pink classifier, and as a reasonable, a good, properly behaved classifier, it should tell that you are looking at target domain data, right? But if that is the end of the story, then you are doing nothing for domain adaptation. Because for domain adaptation, what you really want to do is, at this part, whether you dump in source domain data or target domain data, you want or you do not want to see the difference between cross domain data. Yes or no? Should be no, right? Because if you have the computers captured by the cameras, you reach here. But eventually, you want to recognize the target domain, the computer images from online, right? You will also have the same type of image reach here. But you want to do recognition. So you do not want to see any difference between source and target domain data if they are of the same type, right? And that is why for the domain classifier, they do not do standard backpropagation. What did they do? They want to confuse this green part. They want to confuse your feature. They do not want to tell the difference between source and target domain data if they are of the same type. And that is why they not only have the domain classifier, when they do the gradient descent, they do a gradient reversal descent. They want to confuse your features if they are of the same type but from different domains. They don't want to see the difference. So this is just like what? Just like adversarial training, right? Some of you are familiar with GAN, generative adversarial model, and this is simply the idea of adversarial training. You want to confuse your source and target domain model if they are from the same type of category. So are we okay with this, this design? It's getting warmer here. Okay, so I spend more time here because we will go into the details. We will have exercise for this part. So I want to make sure every one of you, or at least most of you, are okay with this design. Okay, so this for the domain classifier, we do not do standard backpropagation. We add a minus sign, and then we do backpropagation. We want to confuse the feature layer. Okay. All right, so that model was proposed in 2015 in ICML, and surprisingly last year in CVPR, a different group of people, they also proposed a very similar thing, also in terms of adversarial training, try to address the same or similar problem. So that is, okay, so again, this is last year CVPR, last year in Hawaii, Honolulu, a fantastic place. Okay, so in this case, they also want to address domain adaptation using adversarial training. So let's see how they did this. So for the pre-training part, they have source domain data with label, so they can train their feature extractor and classifier. It's simple. For the domain adaptation parts, the thing different is they need to not only have the original labeled source domain data, they also have target domain data. Again, they are unlabeled. They also have the target domain data. You can see it's a handwritten digit data set, but from a different data set. The thing only different is this is a different CNN. The feature extractor part is different. So not like the first one, people share source and target domain data, share the same feature extractor, share the same encoder in this ICML 15 work. In this CVPR 17 work, they have distinct feature extractors. But anyway, their point is the same. They want to confuse the domain label. They have pre-trained encoder for the source domain data. Now they want to train additional encoder for the target domain data, not using any label information. But the point is, they still need to confuse their domain labels. So they still do the domain classifier. They still do the adversarial training. They want to confuse the features so that the feature layer would not be able to tell the difference between the input data depending on their input domains. Okay. So for the training part is complete, the first two stages. When they are complete, for the testing, you can either dump in your source domain data or you can dump in your target domain data because they will reach the feature layer anyway, right? Once they reach the feature layer, then they can ask the last part to do the classification. So that is what this CVPR 17 paper did. And you can see the idea is virtually almost the same as this ICML 15. So I would say they have a solid experiment section, and they are a good storyteller, right? So they can make these things happen again. Okay, so adversarial training for domain adaptation, this is a good idea. Even for sometimes the CM features are not good enough, then you need to make additional things happen to confuse the features across domains. Okay. So domain separation net. So 1 year later, 1 year earlier. So this group of people think, what if we are dealing with more complicated, more complex data? Because in this case, in the CVPR 17 or in ICML 15 paper, these two models only deal with kind of similar data, right? Because they only allow the data of the same dimension, similar types, to dump in the feature extractor. Because for this one, the green one, or for this CVPR 17, they are dealing with digits only. So shared shared encoder or not, they are dealing with more simple, more similar images when they design their feature extractor. But in sometimes, data are more complex. For example, like one of our own works, we are dealing with third-person view data, third-person view video, but at the same time, we are dealing with first-person view video, like GoPro, or some handheld wearable devices. So we are dealing with video data, but the viewpoints are so different. One is third-person view, and the other one is first-person view. So in this case, we do not feel comfortable. We do not think using the same type of encoder would be sufficient in dealing with such cross-domain data. I think these people feel the same way. So they came up with a little bit more complex data, trying to deal with the domain shift. So what did they do? Okay, so let me briefly explain the notations. Again, the superscript H and T indicate source and targets, respectively. And you can see that when they deal with source and target domain data, of course, they dump in the source domain and target domain data into their encoders, but they have two different types of encoders. You can see for the orange or yellow, it's orange, right? For the orange one, it is a shared encoder for cross-domain data. And for source and target domain, they also have their own specific encoder, the private one for the source and also the private one for the target. So think about why they need to come up with such designs. Like I said, if you are dealing with source and target domain data, well, there might be images, but they are from very different viewpoints. They are from very different types of sensors. For example, one is photo, the other is sketch, or different kinds of sensors. Using exactly the same encoder like the previous two did might not be a good idea. And that is why they have shared encoder and also the specific one. You can consider that the shared encoder is to extract the commonly shared content information, right? So like the example I just gave you, maybe we have the face images of photos, we have the face image of sketches. The shared encoder would focus on extracting the content information only, not the color, not some style information. Those color information will be preserved in the private encoders. Does that make sense? So in that way, if you dump in your sketches or if you dump in your face photo images, the orange one will extract the content information only. And if you dump your sketch into the specific one, it will, for example, it will extract the features corresponding to the sketch style. Similar remarks apply for the blue one. If you dump in your photo, the real photos into the private target encoder, it will extract the style features which correspond to the photos. So once you have these features, what would you want to do? Well, if you have photos and sketches of the same person, of the same identity, you want these two features to be as close to each other as possible. It's just like the contrastive laws, right? And for the shared and the private encoder, hopefully these two features will be as similar or different. Different, right? Hopefully this will be as different as possible. Because you want your content to be preserved in the shared encoder, you want your style, background, etc. information to be preserved in the private encoder. So this is why you want these two features to be as different as possible. You want these two features to be as distinct as possible. But taking these two features, eventually you would still like to reconstruct your original data. So it's just like autoencoder. And for the source domain data, because you do have the label information, so you still can ask the classification laws using this branch. So again, it is a multitask learning. We consider, well, they consider data reconstruction laws and the classification laws at the same time to train their models. And the reason why they design their model in this way is they need to deal with, although the data of the same type, but their properties are so different. And that is why they need to design separate encoders to encode the content, the commonly shared content, and also irrelevant content in their private encoders. And again, with the integration of both features extracted, they should be able to do good reconstruction. With the content features to be extracted, with source domain data label information available, they should be able to calculate the classification laws. And with such multitask learning, they can do backpropagation to refine all their encoder, decoder, and the classifier. And that is how they design this domain separation net. So is this okay for you? Okay. Yeah, again, let me know if you have any questions or if anything is not clear to you. Okay, then we can basically skip the next few slides because I already explained the detail, the functionality of each component. So one interesting thing is let's look at the results. So the source domain is the MNIST, one of the data sets, and the other is MNIST M. Okay. What does M stand for? I forgot. Okay. But we are using MNIST this afternoon. So one is MNIST and the other one is. Oh, okay. Well, you will figure this out this afternoon anyway. But anyway, we have the source domain data and the target domain data. So the first column is the target domain. Oops. I'm sorry. The first column is the original image. Okay. And the second column is the data reconstruction using both private and shared feature. What does that mean? That means we take this one and this one to do data reconstruction. So ideally, this image should be exactly the same as our input target domain image, right? So let's see if that is the case. Yes, for this one, for this data set, the second column looks very, very similar to the first one, to the first column. What about the third column? The third column is using the shared features only. That is using the orange ones only. So what did we say about the orange one? It only preserves the content information, not the background, not the style, those kind of irrelevant information, right? So if we take only this orange feature to do data reconstruction, what would you expect in your data reconstructed results? Think about it. It should look like the category of interest, right? Without background, without those kind of irrelevant information. Let's see if that is the case. Yes, the third column looks like those digits without irrelevant information. And the last column, the last column using the private feature only. That is using the blue ones only. The blue ones doesn't contain any content-related information. So if you take the blue one to do the reconstruction, you shouldn't be able to see any category-dependent information. If you do, then you must did something wrong in your model. So fortunately, in the last column, if you take the blue feature to do the data reconstruction, you didn't see any digit information in it. So it makes sense. So you will consider, well, if you use this data set, it is easier because it is it is source. So I should use these two features as example. So this is source data. Let's see what happened to the target domain data. So the target domain data is more challenging, right? They are digits, but with backgrounds with different colors. So again, the first column, original images. The second column, use both orange and private, the blue features to do data reconstruction. So the second column should look exactly the same or almost the same as the first one, right? That is probably almost the case. The second column looks very much like the first one because it takes both features to do data reconstruction. The third column only takes the content part to do data reconstruction, right? So imagine what you would see if you only take the third one, the content information of such complicated images to do data reconstruction. You should get somewhat cleaned images with label information, and that is the third one. So that makes sense, right? And finally, if you take those private features only, you should reconstruct what? The backgrounds. Those totally irrelevant information. So most of the unwanted, irrelevant information will be encoded in the private features. And that is this part of the encoder output. So hopefully this gives you a better idea why sometimes one shared encoder is not enough. We need design separate features encoders. And we need to enforce some of them. We want to enforce them. We want them to preserve, to extract content-related features. And for the remaining ones, we want them to extract the background-related features. OK. So are we good with the DSN, domain separation net? OK. So we have about 15 minutes till lunch. OK. I'll try to make this in time. And the next one, personally, I do not find the result to be very, very promising or very convincing. But anyway, it is also an example of domain adaptation using dealing with source and target domain data. I'm not sure it is readable or clear enough for you from the projector. But anyway, for the source domain data, we have the synthesized toy images. Like this one is a cat, right? This is a synthesized data. And for the real data, for the target domain data, we have the toy model presented in the real background. So what this model would like to do is eventually it would like to see if we can input a noise, just like again, if we can input some random vector, and eventually we would like to generate an image looks like this. We would like to see, we would like to synthesize, we would like to synthesize the data, it looks like a real one. So this is what this model is about. Okay, I know this figure might not with sufficient resolution or might not very clear to you. But anyway, so let's see how this model did this. Well, for the synthetic data, or I should say, when they input the noise, and they also need to input the synthesized data. So they want to make this look like in a real thing. So that is their purpose. So when they train this model, I think some of you, most of you, hopefully you would know this is the GAN, right? It's a generative adversarial net. So this is the generator. This is the discriminator. So you input the noise and the synthetic toy data. You would like to synthesize, output the data. It looks like a real one. But your discriminator needs to tell the difference between them. So this is what this discriminator is about. And what about this T? The model T is a classifier. So this model needs to tell which label, which data, category of this image is. So it's a classifier, to be short. It's a classifier. So once you train the training of this model complete, you will be able to pick a synthesized model, just foreground, no background. Input a noise vector, and eventually you will be able to output a realistic background for this model, and it would look like a real one. So basically, this is the what they did in this case. They start working on, although the purpose is data generation, but you can see the losses, they are still based on classification loss. So I still put them here. One is the discriminator loss, and the other one is the classification loss. Basically, this is the generative model for adaptation. And these are the examples. You can see like they input like a dog, and they can generate the models which look like in the real background. But I think by looking at these images, you can kind of agree with me why you think there is still room to improve in this model. Okay, anyway. All right. Well, we do have limited time. We have 10 minutes or so. I need to move on a little bit faster. This is heterogeneous because, but I think this heterogeneous model requires the understanding of like decision tree, random forest, and deep random forest. So I will see if we can pick any proper time to get back to this model. But anyway, this is a model dealing with heterogeneous domain adaptation. And like I mentioned earlier, for heterogeneous domain adaptation, we need to project the data onto a common feature space, right? That is how we can design, train our, right. That is how we can design a good classifier in this common feature space. Okay, so basically, I still can show you the framework of this model. So basically, we need to train the blue arrows and the orange arrows. That is the feature transformation. We need to transform the image data and the text data onto the same feature space. And with the label information from source and the small amount of label information from target, we want to train our classifier. So basically, that is the idea. We want to find a gray common feature space, that is this part, so that we can train the classifier in this feature space, that is this part. Okay, but of course, the story behind this model is how can we train a good feature space which can be commonly shared by both the data domains. And another thing is how can we train good classifiers? How can we train a good classifier given that only a small amount of data, of label data, is available in the target domain, while most label information is from the source domain. Okay, but like I said, this requires a little bit background in decision tree random forest and deep random forest. So I think I will probably skip this model for now, and we will come back later if we still have time. Okay, so there are a few more examples with classification-based, visual analysis-based domain adaptation or transfer learning. And this is one of the examples. So we are recognizing, or I should say, this is the task of multi-label classification. In case you are not familiar with multi-label classification, that is given an input. Here is an image. Given an image, we need to predict multiple labels at once. Well, you can do that iteratively, sequentially, but anyway, given one input instance, you need to predict multiple labels. And that is the purpose of, or the goal of multi-label classification. But some of you might ask that if you are familiar with object detection, if you have used like YOLO or whatever object detectors, fast RCNN, etc. detectors before, you might be wondering, well, why don't we just apply a bunch of object detectors for this image? Then that would be the end of story, right? But don't forget that in order to use your object detectors, you need to train your object detectors. You need to have a bunch of ground truth data, the object with bounding boxes, so that you can train your object detectors. If you do, congratulations, you can do a very, very good job in recognizing, in detecting each individual object. Because we all know, recently, we have very, very powerful object detectors, like those I just mentioned. But the problem is, in some cases, we don't have the ground truth data to train the object detectors. We just have the data, we just have the images, or we just have the videos. And with some like hashtags, we just have some labels. In those cases, we still want to design a good multi-label predictor for such images or for such videos. Okay. So anyway, so you can consider this as a task of relating image and label domain. Okay, they are still cross-domain data, image or text domain. And one more important thing in multi-label classification, in multi-label prediction, is when we design the model to address this task, we need to exploit label co-occurrence information. What do we mean by that? Think about it. For example, this is a scene of an indoor living room, right? So for an indoor living room, if you see a TV, then you probably will see the sofa or a table at the same time, right? If you have an outdoor scene, if you see an airplane, would you often see a boat or ship at the same time? Probably not, right? So that is what we meant by label co-occurrence. We want our model to be able to automatically exploit, preserve, and to utilize such label co-occurrence information. We don't want to do prediction one by one, individually, independently. Then there's no point to address multi-label classification. You just do binary classification for each label, right? So for multi-label classification, we really want to look into our data, not only to learn the relation between the two domains, but also to exploit the label co-occurrence information. We want to introduce such capability into our learned model so that when we do the classification, when we do the testing, if we have high confidence for certain labels, then for the remaining highly related one, they should have higher confidence as well. That is the purpose. Okay, so let's see how we start looking at this problem. So back in 2017, well, it's just 2 years ago, in AAI, I think we were among the first using deep models to address multi-label classification. And again, for those who are familiar with autoencoder, you would probably tell the green one, the model bounded by the green circle, bounded by the green rectangle, which is exactly an autoencoder. The autoencoder, what is input and output? Well, we have the labels as our input, and for the reconstruction purposes, we have the same labels as our output. What else? Because we are dealing with multi-level classification, our real input is the image. So we have the image of this, because we have these pairwise input. So we need to project this image and this bunch of label information onto the same common feature space, right? So when we train our model, we want the same pair of input, and this pair of input, I mean the image and their ground truth label information. We want this pair of input to be as close to each other in this common feature space. And because we have the autoencoder for this green part, so we want to ensure that whatever feature encoded here in the latent space, it should be reconstructed back to this label information, which would match our original label input. So this is the design for the training part. So once the training is complete, what about testing? In testing, we just throw in our test image, right? Then it goes this feature extraction layer, reaches the latent space, then it goes the data reconstruction, outputs the multi-label at once. So again, this is a, I think, unique combination, a unique integration of two deep models which allow us to train and to address the problem of multi-label classification. Okay, then we can skip this one. This is the one I just mentioned, the training part and the testing part. And of course, it's not the end of the story. This year, 2 groups of my students, they continue to work with multi-level classification. The first group, one of them is Shangfu, it's right here, one of your TS this afternoon. Here we integrate the idea of visual attention and recurrent model. The lecture yesterday was on memory networks, right? So you should be familiar with the recurrent neural nets. So basically, here we integrate visual attention and recurrent nets. We want our nets to be able to memorize, to exploit the information between different labels. That is to exploit the label co-occurrence information. Since you are familiar with recurrent neural nets, you know one of the settings is you need to determine the label order. You need to decide each time step which label to predict, right? And for the multi-level classification case, we don't want to deal with that problem. Somebody say we should do that from A to Z. Other people say we should do Z to A. Who knows? Some people say we should do from the most frequently one to the least frequent, less frequent one, etc. We don't know which one is the best. Then I think the cool idea here is once we integrate the visual attention, we let the visual attention guide us. With more visual attended area, it will output the corresponding label. So I think this is a very unique idea. We integrate the recurrent neural nets and the idea of visual attention model, and at the same time, because of use the RNN model, we are able to exploit the label co-occurrence information. So this is one way we just did early this year at AAAI to do multi-level classification. And the other thing is, I think I need to skip some results. And the other thing is, this year at CVPR, we have another work which is also on multi-level classification, but we also did additional things. Here we additionally consider the semantic information between labels. Some labels are positively related, some are negatively related, or some of them are with some order relation. So we not only learn the relationship between images and labels, we only exploit the information, the knowledge graph from the semantic space. Remember that in the first lecture, in the first few slides, in addition to the instance transfer, feature transfer, parameter transfer, we did mention the fourth one, right? The fourth one is using some prior knowledge, some knowledge graph. So utilizing the knowledge graph would be a powerful technique allowing us to do the transfer. Okay, I just want to highlight this because it would take like another 30 minutes or so to explain the details of this part. Okay, I'm glad I already covered the segmenters, the row-thin segmenters. We want to learn the data from one city, and at the same time, we'll be able to adapt to other cities. So this is the co-work with Professor Sun Ming here at NTHU, and he's now at IPU. Okay, and how we did this? The first thing is global mean matching, right? Using, I should say, the first technique we use the adversarial training to match the global distribution. So I should correct my previous statement. So the first thing we utilize is this ICML model. We utilize the domain classifier. We want to confuse our encoder so that it cannot tell the difference whether or not the image is from Frankfurt or the image is from Taipei. Okay, but this is only global domain matching. And remember that we also want to predict some pseudo labels for the target domain, and hopefully not only global matching, class-wise matching would also help us in terms of this transfer task, right? But the thing is, for the Taipei row-thin images, for the Tokyo row-thin images, we don't want to hire tons of labels to annotate the information for us. So I think one cool thing here is the so-called time machine features in Google Street View. I'm not sure whether or not you have used this before, but Google Street View allows you for some specific locations, you can pick more than one time to extract the Street View because the Google Street View car drove there more than once. So with this Google Street View information feature, you would be able to extract the same thing, but at different times. What can we utilize here? Well, because they are from the same thing, we can do simple matching, image matching. For the matching areas, they probably correspond to static objects, like buildings, roads, and signs, those kind of things. For non-matching areas, they probably correspond to moving objects, like cars, pedestrians, something like that, right? So for the matched areas, we have a higher confidence calling them static objects. Then we not only do domain global matching. For those static objects, we can also do class-wise matching. And that is why we can make this segmenting performance better as well. Okay, so I think this pretty much ends the second part of the lecture. So basically, the second part here, we focus on the classification task, right? Domain adaptation, classification task. And we particularly focus on like semi-supervised or unsupervised domain adaptation. In the first half, we covered a bunch of non-deep-based techniques. And the second half, still using MND or even use domain classifier or adversarial training, we introduced a bunch of deep learning-based algorithms for domain adaptation and specifically for solving different classification tasks. So hopefully you are okay with that. And in the third part, after lunch, we will discuss a bunch of image analysis, image manipulation, image synthesis, also regarding cross-domain data. All right, so any questions so far? Okay, it's lunch break, so let's take a break, and I'll see you at 2 p.m. Yep, okay, thank you.